Zeros and ones, the two states of the binary system that can represent things like yes, no, true, false, and of course, on or off. Welcome back to Learning with Merit. I am Mr. Merit, and today we're going to take a bite out of the binary. Before we talk about binary, we need to review the system that many of us have already learned. It's the system that we use for regular math whenever we are working with algebra or arithmetic. It is called the decimal system, and this system is base 10. It is based on the digits 0 through 9. And if we look at the places for this system, it is of course based on powers of 10. 10 to the 0, 10 to the first, 10 to the second, 10 to the third. This would be the ones place, the tens place, the hundreds place, and the thousands place. We could also look at the fractional part of this over on the right-hand side. So we add a floating point. And on the fractional side of this, we have 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, and of course so on. This would be 1 over 10, 1 over 100, and 1 over 1,000. So those are our fractional parts of the decimal system. So what we know from this system is, let's say that we have the number 502. 502 means we are going to have 5 hundreds, we are going to have 0 tens, and we are going to have 2 ones. Now, if we remember this basic system here, we can apply the same principles to binary. Instead of tens, though, we will use a different value. We will use 2s. All right, let's talk about the binary system here. The binary system is different from the decimal system in that it is base 2, meaning everything is based on 2 values. These 2 values are our digits here, and that is 0 or 1. 0 or 1 can be used to represent anything with 2 states, like yes or no, true and false, obviously 0 and 1, and most importantly, on and off. On and off is actually how the data is stored inside of the computer. If we take a 0 or a 1, this is called a bit, and it is the smallest form of data that we can store within the computer. Now, unfortunately, bits are not very useful by themselves, so we are going to package them. If we take 8 bits, this is called a byte. 8 bits equals a byte. 4 bits also has a name. This is called a nibble. Now we're going to take a look at the places in the binary system. If we look at our powers of 2 here, since it's base 2, we have 2 to the 0, the first, second, third, fourth, fifth, sixth, and we're going to stop at the 7th. And the reason is this is 8 values here. These 8 values make up 1 byte. Our values are going to be 1, 2, 4, 8, 16, 32, 64, and 128. So if we take all of this together, and let's break it up just a little bit here, these values are our places for the binary system. So we might write a number like this. We might have 0, 1, 1, 0, 0, 1, 0, 1. And this is a binary value for us. And of course, that means we have a 1 in the ones place, a 1 in the 4s, a 1 in the 32s, and a 1 in the 64ths. If we want to look at the fractional part, I'm going to draw a little line here. We'll look at the fractional part where we add a floating point. 2 to the negative first, 2 to the negative second, and 2 to the negative third. We'll add those. And this is going to be 1/2, 1/4, and 1/8. Now, the reason why we might bring this up is just like in our decimal system where we have numbers like 0.33 repeating, our computer can't actually store values that are infinite. So it occasionally will end up with issues whenever it comes up with an irrational value like that, where we have 0.1 plus 0.2. We would expect to get 0.3, but the computer actually adds on some zeros, and we eventually get round to a 4, like that as we come around. So it's important to understand that this system is imperfect in some ways, but it works very well for computers. All right, we're going to try our hand at converting some decimal values into some binary values. And the first thing I'm going to do is I'm going to write out the first 8 places for our binary system. Now, that is going to be the first 8 powers of 2, or 1s, 2s, 4s, 8s, 16s, 32nds, 64ths, and 128ths. And how did I get that? I just kept multiplying by 2 every time. I'm going to draw a line in between these so I can keep the places straight as we go. Now, the largest value that I can represent in this is a single binary byte. So I'm going to write that down. I'm going to say binary byte. And the largest decimal value is going to be 255. That is the largest value that I can represent here. So what we're going to do is we're going to try and convert the number 13. This is the simplest way to do this. So if we look at the number 13, I'm going to say, all right, which one of these places over here to the right will go into 13, which is the largest one? Well, that is going to be the number 8. So I'm going to put a leading 0 in all of the places that won't go into 13. I'm going to put a 1 in the 8 spot. Now what I'm going to do is I'm going to say 13 minus 8. That will leave me with the number 5. Will 4 go into 5? Yes, it will. So I'm going to subtract 4, put a 1 in the 4's place, and that will leave me with the number 1. Will 2 go into the number 1? No, it will not. So I write a 0. Will 1 go into the number 1? Yes, it will. So I'm going to subtract 1. That leaves us with a final of 0. And a 1 there. So 13 in decimal is going to be 1101 in binary. Now we're going to try another value here, a little larger one this time. So we're going to do 172. I'm going to say, is 128 going to 172? Yes, it does. I'm going to write a 1 there. We're going to write 172 minus 128. And that is equal to 44. Will 64 go into 44? It will not, so I add a 0. 32 will, though, so we're going to subtract 32, add a 1 in the 32 column. That will get us down to 12. Then will 16 go into 12? No, it will not, so we add a 0 there. We subtract 8 because 8 will. And now we have 4. We're going to put a 1 in the 4's column and subtract 4 because 4 will go into 4. And that finally leaves us with 0 left over, so we fill in zeros at the end. So 172 in binary is 1010 1100. Sometimes we need to convert from a decimal value into a binary value. And one way that we can do that is using the divide by 2 method. Now what this is, let's say that we need to convert the value 97 into binary. So I'm going to divide by 2 and keep track of the remainder to build my binary number. So I'm going to do 97 divided by 2. That gives me 48 with a remainder of 1. So I'm going to write that 1 down here at the bottom. Then I'm going to divide by 2 again. That gives me 24 with a remainder of 0. So I'm going to write my 0 down there. Divide by 2 again, I get 12. Again, a remainder of 0, so I'm going to write it. Divide by 2 again, I get 6. Write another 0. Divide by 2, I get 3 this time. Again, still a remainder of 0. Then I divide by 2, and this time I get 1, but with a remainder of 1, so I write a 1. Then I do divided by 2 for a final time, and this is going to give me 0 with a remainder of 1. And so here is my binary number for 97. Now we're going to take a look at how to go from a binary value to a decimal value. Let's say that we have the binary value 1, 1, 1, 0, 0, 1, 1, 0. Now, a quick trick that can kind of be helpful is you can check if you have a 1 in the ones column here, then you will have an odd value. If you have a 0, you'll always have an even. So you can sort of check your value whenever you're doing that. The easiest way that I think that you can go about this is just go and find the ones places. So there's 1 there, 1 there, 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 and there. Take the place that they are in and add them all up. So we're going to do 128 plus 64 plus 32 plus 4 plus 2. And if you add all those values up, what you get is 230. And so 111,00110 in decimal is 230. Let's try another one here. Let's say that we are given the value 110, 1100, like that. Now, we can leave this place out, or we can add a leading 0 there if it helps us keep track of what we're doing. But we always want to proceed from the right to remember our places, just like we would in the decimal system. So here we're going to add up all of the places that we have. We have 64, we have 32, we have 8, 4, and that is it. If we add up these values, we should get 108. So 1101100 in decimal is equal to 108 or 108. Sometimes we need to convert binary values such as this one right here into decimal values, and one of the ways we can do this is called the multiply by 2 method. So what we're going to do is we're going to take the first bit here, the first number 1 there, and we're going to multiply that by 2. So we're going to say 1 times 2, and we're going to add the next bit. The next bit is a 0. This will give us 2. We're going to multiply by 2 again. This time we are at the 0 there, so we're going to 2 times 2 plus the next bit. The next bit is a 1, so we add a 1. This gives us 5. Now we're at that 1. We're going to do 5 times 2 plus the next bit. The next bit is a 1. This gives us 11. Now we're at that 1. 11 times 2 plus the next bit, it is the 0 there, so we do 0. This will give us 22, and now I'm going to move down here. So we're going to do 22 times 2. We're at this 0 right here. The next bit is a 0, so we add 0. This will give us 44. Now we're at that 0 right there. We're going to do 44 times 2 plus the next bit, which is a 1. So this gives us 89. And finally, we're going to multiply by 2 for the last time and add the next bit. So we're going to multiply 89 by 2 plus the final bit here. Once we get to that final bit, we're done. We're adding the 0 there, and this gives us a final answer of 178. This is our final decimal value for the binary 10110010.